All right, let's start with number 1 here. We're looking at our inverse matrices and matrix equation homework. So just a couple of reminders. One is the multiplicative identity. That means when we take any number times 1, that is equal to that number. It keeps its identity under multiplication. The additive identity is this 0, because if I take any number and add this time 0, I still get that number back. All right, going over to number 2 here. It wants us to verify that AI3, remember I3 is the identity matrix for a 3 by 3. So that's 1s in the diagonals and then 0s above and below. And so what we need to check is that if we multiply that, again, you need to make sure you multiply it on both the right and the left, we should get A back. So if we're checking on that, well, it does say matrix B, but really we're talking about, we can relabel that as A. So we want to take 1, 9, 11, negative 3, 5, negative 6, 4, 3, negative 4. And we want to multiply that times that identity matrix. And this is always a good check to make sure that we are doing our multiplication correctly. And so what I mean by that is we take our first row times our first column, which is kind of cool because it's all those zeros. But we're going to take 1 times 1, that's 1. Then negative 3 times 0, that's just 0. And then 4 times 0, that's also just 0. So all we're going to be left with is 1. And then we do that again. Same row, but we move over to the next column. And so again, multiplying by those zeros is going to make everything become 0, except for when we multiply negative 3 times the 1, we're going to get negative 3. And so we keep doing this process, the row times that last column. And again, the only one that's going to work out to be a number is the 4 times that 1. So we're going to get a 4. And then we start all over again. So we'll do the second row this time. And we'll multiply by that first column. 1 times 9 makes us get 9. Then we'll multiply that row times that column. And again, the only one that's going to get us something is going to be that middle guy, which will be a 5. And then lastly, that same row times that last column is going to just do the 1 and the 3, which will make 3. Because again, everything else will be 0. We multiply 11, negative 6, negative 4. It's just going to get us the 11. And then again, that row times that column is going to get us the negative 6. That middle one's the only one that's there. And then lastly, the row times it's going to get us the negative 4. Okay, so you can see that it checks back and gets us our original starting matrix. So to go the other way, we're going to write the identity matrix first and multiply by our matrix 1, negative 3, 4, 9, 5, 3, 11, negative 6, negative 4. And we start a row times a column. And again, you can see the only one that's going to make a number is those first ones, which will make 1. Then multiply that row times the next column, and the 1 with the negative 3 is going to pop out. And then last times that last column, we'll get 1 times the 4, because everything else just becomes 0. And so hopefully you can see the pattern that's happening. 0, 1, 0. When you multiply times that first column, the only thing that's going to pop out will be our 9. We multiply it times that second column, we get a 5. And the last column, we get a 3. Then you move to the last row there. First column, it's going to be the 1 and 11 because everything else is 0. Multiply it times that second column, you'll just get the negative 6. And the last column, you'll get negative 4. And so as you can see, we get our original matrix back again. So the identity is working out there for us. All right, for number 3, we want to determine the inverse of this given matrix. Since it's a 2 by 2, we can use our little formula that we determined in class. So this is equal 1 over the absolute value of the determinant of A. And then the matrix, we are going to flip-flop that diagonal, and then we'll change the signs of the other diagonal. And so the determinant of A is multiplying -4 times 5, so -20. And then minus 6 times -3 is -18. So really this is -20 plus 18, which is -2. But it wants the absolute value of that, and so we're going to get a 2 there. So really for our inverse, we're going to have 1/2 times 5, 3, -6, -4 is that matrix. But you could rewrite it if we could distribute that 1/2 through that little scalar number. So it'll be 5/2, 3/2. -6 times 1/2 is -3, -4 times 1/2 is -2. So that is going to be the inverse. Again, you could use either one of those. So number 4 wants us to check if we're going to take a matrix times its inverse, this better equal the identity, and it's a 2 by 2 identity. So that's going to be that 1, 0, 0, 1. And again, it wants us to check both ways, make sure that we're getting that identity. So if we take matrix A, which is -4, -3, 6, and 5, we want to multiply it by a inverse, which you can use either one of these. You can use the one with fractions, or you can use the one that doesn't have the fractions and then multiply by 1/2, however you want to do that. I think that it was kind of getting easier to do it that way. So I'm just going to write this matrix part here. This isn't the whole inverse. We'll need the 1/2 still, so I'm just going to stick the 1/2 at the end, and that's fine. So I'm going to multiply the first row and column, so that's -4 times 5 plus -3 times -6. That's my first entry. Then I'm going to take that row and then times the column, so that's -4 times 3 plus -3 times -4. Then we move on to the second row and again multiply times the first column, so that'll be 6 times 5 plus 5 times -6. And then the last one, we'll do 6 times 3 plus 5 times -4. Now at this point, because we've been doing this multiplication, but we've also been finding determinants, make sure that you are adding these terms that you're finding. That is different from the determinant, which is actually that subtraction. Okay, so just be careful with our signs. And so if we take all of this, and then we still have that times 1/2. So what is this? Well, we have -20 plus 18. So -20 plus 18 is -2. Here we have -12, and then that's a positive 12, so we're going to get 0. And then we have, let's see, this is going to be 30 and -30, so that's 0. And we have 18 minus 20, so that's -2. Okay, and so we have this -2, 0, 0, -2. And I actually realized I wrote something down incorrectly earlier, so let's go back over here for a second. That I wrote this, I wrote absolute value of determinant of A, but really what I like to write is just that notation, but that just means determinant of A. So we're not actually taking the absolute value of it. Not sure why I was thinking that. So I'm going to kind of go back and erase that absolute value. And so it is that -2. So let's make sure we have that correctly on there. And so this would be a -5/2, -3/2, and it would turn into the bottom two being positive. So +3 and +2. So just want to make sure that that's okay there. So when we have that -1/2 over here and over here, it should be negative. So make sure we have that. So times -1/2. And that will actually turn into 1, 0, 0, 1 that way, which is what we needed to have happen. So that was actually a nice check that I had that error in there. So let's go the other way to make sure it also works. So A inverse times A. So again, A inverse is that -1/2, 5, 3, -6, -4. And our matrix A was -4, -3, 6, and 5. So we'll take the row times the column. So this is going to be 5 times -4 plus 3 times 6. And then 5, 3 times -3, 5. That's going to be positive 5 times -3 plus 3 times 5. Then we move to the second row, first column. That's going to be 24 plus 24. And minus 24. I need to show my work on this. Sorry about that. So it was negative 6 times negative 4. And then plus, this was a negative 4 times 6. Did I go too fast? Make some errors. Let's slow down a little bit. We have negative 6 times negative 3 plus negative 4 times 5. So this whole thing times, we still have that negative 1/2. So negative 20 plus 18 is negative 2. Negative 15 and 15 is 0. 24 and negative 24 is 0. This is 18 and negative 20, that's negative 2. Again, times the negative 1/2 with each entry gets us 1, 0, 0, 1, like we expected, which is the identity. All right, number 5, solve the system using the inverse of the coefficient matrix. So remember, we could write any system in this way where A, X, and B are matrices. So matrix A is the coefficient matrix. So we have negative 4, negative 3, 6, and 5. The matrix X is a column matrix with the variables that we have going on. This will equal the constants, negative 4, 8. Okay, so if we want to solve this equation, what we said is we could take A inverse, let's see, so this is what we're talking about, AX equals B. If we take the inverse of A and multiply it on both sides, we already know that the inverse times A is the identity. And when you multiply the identity times any matrix, you just get that matrix back. So if we want to solve for the variable column matrix, we know that we just need to multiply A inverse times B. Well, we know that this is matrix A, and we already found A inverse actually. It was the 1/2. Let's go back over here. It was the negative 1/2, 5, 3, negative 6, 4. So negative 1/2, 5, 3, negative 6, negative 4. So if I multiply A inverse times B, I'm going to write negative 1/2, 5, 3, negative 6, negative 4 times B, which is negative 4, 8. So what that looks like then is the row times the column. We'll do 5 times negative 4 plus 3 times 8. That's that first entry. There's not another column, so that's the end with that part. So we move down now to the second row with that column. So negative 6 times negative 4 plus negative 4 times 8. So that's our matrix. We'll multiply by negative 1/2. And we have negative 20 plus 24 here. 24 minus 32. That'll be negative 1/2. Negative 20 plus 24 is 4. And 24 minus 32 is negative 8. So we multiply that by negative 1/2. That's going to be negative 2, 4. Which tells us that X is negative 2 and Y equals 4. And so if I were you, I'd want to go back and plug this into the very original system and make sure it works. So again, X equals negative 2 and Y equals positive 4. So I'll just check the first one. Negative 4 times negative 2 minus 3 times 4 is supposed to equal negative 4. So this will be 8 minus 12, which does equal negative 4. And then check it in that second one just to make sure. All right, 6 and 7 are review questions. So let's see. Number 6 here, it wants us to determine the vertex and sketch the graph for this function. It has a power 2 on it, so I know that it's a quadratic, which quadratics look like that U shape, but there's some transformations that are happening. The negative here reflects over the x-axis because it's making all our outputs become opposite signs. We have a vertical stretch by 2. We are shifting to the right 4 spaces because it's going to subtract 4 from every input, so we need to increase our x values, and it's going to go up 2. So that right 4 up 2 is actually helping with our vertex. It would be at 4, 2. So to sketch that, 1, 2, 3, 4 up 2. and it is upside down, so I know it's going to be going that way, but it's being stretched by 2. So normally the graph will go left 1, down 1, right 1, down 1, but because we're being stretched, it's going to go down faster like that. And if I want to like check that those are right, you can always double check that these points are on the graph. So this is 5, 0, and 3, 0. That's 4, 2. All of them should satisfy that function. Now it does say find the x-intercepts, and so I can kind of see them right there actually. That's nice. They're 3, 0, and 5, 0. But to verify that algebraically, we're trying to see when -2 times x minus 4 squared plus 2 is equal to 0. So if you solve that, we can, we're trying to isolate x, we get -2 over, we get -2 times x minus 4 squared equals -2. Divide by -2 on both sides because you're trying to get that guy gone. So this would be x minus 4 squared equals +1. You take the square root of both sides. When you do that, it will cancel that squaring, then does that, but we're going to get 2 roots here. It's both the plus and the -1. So we have that x minus 4 is equal to the +1 and x minus 4 is equal to the -1. If we solve this, add 4, we get x is equal to 5. Add 4, we get x equals 3 like we expected. So that's just showing algebraically that our graph was good. All right, the next thing we want to do is determine on intervals on which the function is increasing. So we are increasing, you got to look at it from left to right. Right here on this portion, as you keep going up, your y values are increasing as your x values are increasing. So that would be from -infinity, because it's going to be going really left forever. We read it in terms of x, up until an x value of 4. And we put a parenthesis on that because nothing's really happening at 4. That's just where the change from increasing. But you can't say it's like increasing really at that point. So we normally don't put brackets on there. Then to get where it is decreasing is going to be the other portion, which in interval notation, that's going to be from 4 to infinity. For our domain here, it goes left and right forever, -infinity to infinity. In our range, it goes down forever, all the way up to a y value of 2, and it does touch at 2. So we'll have that bracket on there. All right, last thing we want to graph is e to the x minus 2, which I kind of covered up with my earlier problem. So this is really the e to the x function shifted to the right 2. That -2 is up with the x, so that's how I know it's shifting to the right 2. So what I like to do is make a teeny tiny table, maybe put in 1, 0, -1 for the parent function e to the x. So when I put a 1 in there, that's e to the 1. That's about 2.7. I put a 0 in there. That is equal to 1. And then e to the -1 is going to be 1 over e, which is about 0.37. So if I plot those on there, I'm going to draw this parent function first. At 1, I'm close to 3. At 0, I'm at 1. And at -1, I'm below a half. And I know I have this horizontal asymptote because if I plug in exponents to e to the x, it will never go negative. So this right here is my parent function. This is e to the x. So if I'm going to shift to the right 2 spaces, I'm just going to take all my points and move right 2. And so you can see that shift. It should look exactly the same, but move to the right 2 spaces, and it has the same horizontal asymptote, which is going to be at y equals 0. So this is e to the x minus 2. So my domain is -infinity to infinity, and my range, it goes to 0, but doesn't actually touch there to infinity. That's why we say that there's that horizontal asymptote. All right, hope that helped.